Up until 15 years ago, oceanographers were heroic figures who went to sea, grew beards, and worked with relatively simple instruments, such as plankton nets, water samplers, thermometers, and bottom corers. Data processing was accomplished by visual observations, and data recording required only the sophistication of a pencil and a notebook. By the late 1950s and early 60s, however, the critical needs of both the military and civilian communities for complete and more predictable information about the oceans required that these classical approaches be supplemented by a new type of oceanography. The new breed of oceanographer utilizes unusual vessels, low-flying aircraft, electronic data collection devices, and high-speed electronic computers in the course of their daily work. And whereas traditional oceanography based its models of circulation and distribution on seasonal surveys and long-term statistics, the new oceanography collects data several times a day from hundreds of different data platforms. This simultaneous collection technique is known as the synoptic approach, and it reveals the shifting, highly complex patterns which are almost completely obscured by the old averaging process. 3 new oceanographic prediction systems which make use of the synoptic approach were developed by the Naval Oceanographic Office. The Sea Ice Forecasting Program, the Wave Forecasting Program, and Asweps, the Anti-Submarine Warfare Environmental Prediction Service. The Sea Ice Forecasting Program is not to be confused with the International Ice Patrol. This cooperative venture between several major shipping nations was set up many years ago as an iceberg warning system. But starting in the late 40s, the Naval Oceanographic Office was called upon to support various Arctic operations with reconnaissance and forecasting services pertaining to sea ice. These requests came about because of the tremendous sea lift operations required to establish and maintain such Arctic bases as the Thule Air Base in Greenland and the distant early warning sites. The Military Sea Transportation Service had to know not only the optimum routes to take, but also the dates when the offloading sites would become ice-free in order to minimize costly delays in resupply. Similar information about conditions in the Western Arctic were also of value to commercial steamship operators serving Alaskan cities and aircraft flying the Great Circle polar routes, which needed ice boundary data to formulate possible ditching plans. A new and more specialized demand for ice intelligence and prediction services came along late in the 50s to support the under-ice cruises of the U.S. nuclear submarines Nautilus, Skate, Sargo, and Sea Dragon. Data concerning the outer limits of the ice packs was even more important to the subs than to surface ships. And the submarine commanders were also concerned with ice thicknesses because surfacing through thick ice could severely damage the hull and topside instrumentation. In addition, other totally new information, such as the size and frequency of discrete openings and the probable draft of underwater ridges, became of vital importance. To meet these varying needs, Navoceano developed and is developing several ice programs which utilize advanced techniques and hardware. The basic program is the ice forecasting for MSTS and fleet operations. Raw data collected from a variety of research platforms are transmitted directly to the utilizing activities for immediate usage. Simultaneously, they are transmitted to Forecast Central at headquarters in Suitland, Maryland, where the data are converted into ice forecasts. The various forecasts are then transmitted to the utilizing activities. Among the data collecting platforms utilized are aerial ice reconnaissance aircraft, shore stations, drifting flow stations, vessels transiting sea ice, nuclear submarines, and Earth satellites. Because of the need for a synoptic or quasi-synoptic approach, which requires the gathering of a great deal of information in a short period of time, ice reconnaissance aircraft have formed the backbone of the sea ice forecasting services. Trained Navoceano observers aboard such aircraft make visual sightings of flow size, ice age, ridge count, ice boundaries, concentration, water openings, and puddling. This information is transmitted directly to the utilizing activities and also to Forecast Central for conversion into ice predictions. Icebreakers and other reinforced surface vessels provide the more detailed data regarding ice thickness and other close-up physical properties. While nuclear submarines transiting under the ice can supply a continuous profile of all features below the waterline of the ice-water canopy. Basic data pertaining to ice drift predictions, formation and deformation, are obtained from man-drifting ice stations. As an example, Navoceano maintained observers aboard ARLIS II, the ice station sponsored by the Office of Naval Research. ARLIS II meandered 5,300 nautical miles over a 4-year period from 1961 until the spring of 1965. In addition, experimental, portable, automatic weather stations were set up to radio back data on air and ice temperatures, barometric pressures, wind speed, and wind direction. Unmanned stations set up on ice floes also transmitted signals used to determine their location. As a first step toward utilizing weather satellites as data platforms for ice forecasting, Navoceano participated in the TIREC project, a joint effort with the United States Weather Bureau and the Canadian government. Aerial ice reconnaissance photographs were taken concurrently with photographs taken by TIRES II during its passage over the partly ice-covered waters of southeastern Canada. Composite mosaics were constructed of the aerial and satellite photographs to determine if ice boundaries and features could be accurately distinguished from the satellite information. The results were encouraging, and work is continuing on this study project. All information from the various data platforms, as well as supplementary meteorological data from the U.S. Weather Bureau, is received at Forecast Central on high-speed teleprinters. As a first step toward computerizing the ice forecasting operation, the old ice message is being converted to a numerical code. All of this environmental information then goes to the ice forecaster, who reviews it in relationship to other data, such as the preliminary ice reconnaissance chart, the latest 30-day mean sea level weather charts, both observed and predicted, and the observed and predicted departure from normal weather charts. Since ice forecasting is still partly an art as well as a science, the personal experience of the forecaster is a vital factor in accurate predictions. As a cross-check on his own interpretation, the forecaster also refers to historical information from ice atlases, seeking years in which conditions were similar to the current one. The Naval Oceanographic Office provides a number of published forecasts in support of Arctic operations, including the Long-Range Ice Outlook, 30-day ice forecasts, which are issued every 15 days, thus providing a 2-week overlap of information, 5-day ice forecasts, and 48-hour forecasts. On request, specific ice routings are also provided to individual ships and convoys of the military sea transportation service. In 1964, the ice program was extended to the Antarctic by instituting a similar program in support of Operation Deep Freeze. Operation Deep Freeze is the Navy's logistic support for the American scientific probe into Antarctica and has been described as one of the greatest peacetime logistic efforts in history. Primary offloading base is McMurdo Station, located on Ross Island. From here, the annual resupply of scientific studies in the interior of the continent is conducted. As in the Arctic operation, long-range forecasts are prepared. These are supplemented by 30-day forecasts, which are transmitted to shipping via radio teletype. In recent years, operational short-range Arctic ice forecasts have been turned over to the Naval Weather Service. Navoceano continues to make short and long-range forecasts for both the Arctic and Antarctic to improve techniques. Another ice program is Project Bird's Eye. Originally set up to provide the data on water openings needed to support the under-ice transits of our nuclear submarines, the Bird's Eye aircraft has become a flying laboratory for long-range basic research. 9 to 10 missions a year are flown on tracks between Argentia, Newfoundland, Thule, Greenland, Eielson Air Force Base, Fairbanks, Alaska, Bodo, Norway, Keflavik, Iceland, and back to Argentia. Its objectives are the improvement of ice-observing techniques such as the use of the World Meteorological Organization numerical code and development of new procedures for the ridge and water feature count. Also under development and test are new procedures such as moonlight reconnaissance, radar tracking of ice drift, and new systems of Arctic navigation. Project Bird's Eye is also constantly testing and evaluating new equipment and instrumentation, such as infrared temperature sensors and buoy tracking and interrogation devices. All of these objectives have as their ultimate end the development of historical atlases and the refinement of forecast techniques such as convergence, divergence prediction, water openings forecasting, ridge forecasting, and the adaptation of these techniques to computers. Wave forecasting is the second major oceanographic prediction system of the Naval Oceanographic Office. The concept of navigating with the weather is not new. In 1847, Matthew Fontaine Maury gathered the logs of a number of ships and used these observations to prepare wind and current charts which indicated the best tracks for various voyages and enabled captains who followed his advice to cut their round-trip times in half. However, the use of synoptic and prognostic wave charts and long-range forecasts as navigational aids is new. The need for such charts first became apparent in planning the activities of various oceanographic survey cruises in the early 1950s. With accurate forecasts, survey work could be scheduled according to expected wave conditions and locations chosen in the most favorable areas for operation. Other applications for wave and swell data soon became apparent. These include, among many others, ship routing for optimum speed, passenger comfort, or cargo safety, the testing of newly designed ships under specific conditions, determining the sonar quenching effects of high wave conditions, and improving the design of breakwaters to reduce coastal and beach erosion by wave action. The three major factors in wave prediction are wind speed, wind duration, and the length of the fetch. since all of these factors are meteorological. Both the synoptic and prognostic wave charts are prepared as overlays to weather charts. The bulk of the data used to prepare the charts comes from shipboard observations and consists of barometric pressure, wind velocity, and observed wave heights. However, most operational wave charts are computed from the observed barometric pressure patterns. Both the synoptic and prognostic charts are distributed to the users by radio facsimile broadcasts. This operational function has been turned over to the Naval Weather Service, but Navoceano still prepares the charts on a developmental basis to improve existing wave prediction techniques. For the same reason, the bulk of today's optimum ship routings for military and military-leased vessels are handled by the Naval Weather Service. But Navoceano still prepares a small number each year. A particularly interesting example is the request from NASA to prepare the routings for the barge Promise, which transports the giant Saturn boosters down the Mississippi from Huntsville, Alabama, through the Gulf of Mexico, and up the Atlantic coast to Cape Kennedy. Because high seas could twist the precision booster out of alignment, NASA depends upon wave predictions and routings to assure a safe trip. While such assignments are topical and exciting, other vital research projects are aimed at improving basic knowledge. Typical of these is Argus Island, a research platform of the Office of Naval Research situated in the open ocean 22 miles from Bermuda. Located here are the basic instruments of oceanographic research. Numerous experiments on ocean currents, waves, and temperature are carried out simultaneously by various agencies. The current meter measures both direction and velocity of currents at selected ocean depths, with a readout in the recording laboratory. Concurrently, a thermistor chain measures water temperature at these depths and provides data for another recorder. The wave staff, one of the very few open ocean wave meters whose accuracy can constantly be checked, also transmits data to the laboratory. Here also at Argus Island, direct measurements are made of the energy transfer from wind to water and water back to air by measuring both the vertical and horizontal components of the wind. Another special research project utilizes sensors to measure both direct solar and reflected radiation. Another project is SWAP 2, an experiment in aerial stereophotography to determine how wave energy is distributed over wave period. To obtain the three-dimensional aspects of waves, 4 aerial reconnaissance aircraft take simultaneous pictures, 3 at an altitude of 4,500 feet and 1 at an altitude of 9,000 feet. Later, stereo readers pick off the wave heights in relation to the local sea surface elevation, and mathematical analysis of the energy transfer is possible. Since synoptic and prognostic wave charts are prepared every 12 hours for use during the following 24-hour period, the time required for their preparation is a definite limiting factor in their useful life. While computer techniques are now being used by the Naval Weather Service to prepare operational charts of calculated wave values, Navoceano is developing a new mathematical wave model which, in conjunction with numerical wave reporting techniques, allows the use of high-speed computers and XY plotters for use with observed rather than purely calculated values to permit more accurate prediction of the wave field. Asweps, the Anti-Submarine Warfare Environmental Prediction Service, is the newest and most comprehensive oceanographic prediction system developed by the Naval Oceanographic Office. Established originally in the late 50s as a feasibility study to determine if thermal conditions affecting the performance of ASW sonar could be predicted, Asweps has grown to encompass a great many other oceanographic and meteorological factors. The knowledge gained through this program will be of inestimable value not only to military tactical planners, but also to meteorologists, marine biologists, and oceanographers doing pure research on the basic structure of the sea. One of the first projects was the construction of a sea surface temperature model which showed that the sea surface temperature pattern was composed of a series of alternating warm and cold water masses, or filaments. Conventional long-term statistics could not predict such widespread short-term variability. As with meteorological, wave, and sea ice forecasting, it was necessary to adopt the synoptic approach. Since sea surface temperature observations were obtained mainly from synoptic meteorological observations by naval and commercial ships, and these were seldom dense enough to permit realistic analysis, data for a longer period of time had to be combined. Another important factor was the vertical thermal structure of the ocean, which greatly affected the performance of sonar. However, the mechanical bathythermograph was then the only oceanographic instrument commonly available for use by ships at sea to measure seawater temperature at various depths. This limited the number of BTs received. In order to overcome these data deficiencies, development programs on new techniques and hardware were begun. First, a general model between the sea surface temperature and the vertical temperature structure of the ocean was developed. This made it possible to prepare a general layer depth chart on the basis of sea surface temperature patterns with the relatively few available BT reports. Then an airborne radiation thermometer was developed, which measures sea surface temperature by infrared radiation. Mounted aboard research aircraft, it provides a great number of sea surface temperature observations in a short period of time. Another piece of hardware which has been developed is the airborne expendable BT. Dropped from the aircraft while in flight. This expendable device measures temperature by releasing a probe which sinks to a depth of 1,000 feet. Then radios the data back to the aircraft. With this equipment, a great deal of information can be gathered over wide areas of the ocean in a relatively short time. A parallel development is the shipboard expendable BT. This lightweight device can be used from ships cruising at speeds up to 25 knots. To obtain temperature profiles with depth to 1,500 feet. The cost is relatively low, and in addition, this new unit offers an improvement in accuracy over the mechanical BT. An instrument designed to improve the quality and quantity of sea surface temperature observations by commercial and Navy ships is the near-surface reference temperature device. It consists of a thermistor probe mounted in the ship's seawater injection intake. With a meter readout located in the engine room or on the bridge, temperatures can be measured from 37 to -2 degrees centigrade with an accuracy of plus or minus 0.2 of a degree. Another new development carried aboard the Asweps aircraft is the Airborne Wave Profiler. This radar device measures the heights and wavelength of ocean surface waves and presents the information in hard copy form. The NOMAD buoy is an anchored buoy station which measures wind velocity, air temperature, barometric pressure, and ocean temperatures to a depth of 1,000 feet. It records all this information and then at set intervals transmits it to shore stations. The Asweps buoy system is designed to consist of a network of such buoys. Concurrent with the hardware program is the investigation of several prediction models. The most complete model is based on the three-dimensional current structure of the ocean. It involves 100 points equally divided to area and 30 layers in depth. This cube is surveyed, predictions made, and then resurveyed 10 days later for verification of the predictions. The model is an attempt at establishing the heat budget for this particular cube of ocean, taking into consideration the heating effect of the sun, the loss of sensible heat through back radiation, convection, and evaporation, and the mixing effect of high winds, which creates the mixed layer depth, the transition zone between fluctuating temperatures of the surface water and the relatively stable temperatures of the deep water. A second short-term model combines heat budget and wind stress to provide 5-day forecasts of layer depth and sea surface temperatures at a series of points. Because all of these models involve large masses of data, numerical codes and computer techniques are utilized to reduce preparation time. Already, certain of the operational charts are machine prepared. The Objective Sea Surface Temperature Analysis Program is a good example. SST data is transferred to magnetic tape, processed and averaged at 12.5-mile grid points. Hand editing is eliminated, and the computer is programmed to reject data obviously in error. The printout is made either in numerical form or by a curve follower. Evaluation studies of the various programs indicate that good progress is being made. In March of 1964, SST data recorded by a thermistor probe in the seawater intake of the oceanographic vessel Gillis were compared with interpolated sea temperature values from facsimile charts compiled for the period of the Gillis cruise. 69% of the Gillis observations deviated less than 2¼ degree occurred in the areas of maximum thermal gradients where there was a great complexity in the SST field. Large portions of the ice and wave prediction systems are already operational, and the Asweps field operational evaluation commenced in April of 1966. Its new group, the Oceanographic Air Survey Unit, coordinates all aerial observations of ice, waves, and thermal structure. Meanwhile, the U.S. Naval Oceanographic Office has moved on to other projects. Projects which may lead to such things as the use of polar sea routes for commercial shipping and the economic exploitation of the seas.